In this lecture, we will extend the Lyapunov stability theorems that we have studied for continuous time systems to the discrete time case. Okay, so let's quickly remember what Lyapunov stability theorem was for a continuous time system. Suppose that we have an autonomous system, x that equals f of x. Okay, f is a mapping from Rn to Rn, so we're talking about an nth order system if, and suppose that the origin is an equilibrium point of this system if you can find a positive definite function, okay, from Rn to R, such that the time derivative of this function along the solutions of this system, you look at that, and if it's negative semi-definite, then we conclude that the origin is a stable equilibrium point of the system. If it's negative definite, if the time derivative is negative definite, then we conclude that the origin has to be asymptotically stable. If the time derivative v dot is negative definite plus this function v is radially unbounded, then we have the globally asymptotically stable case. Okay. Now what we're going to do is we're going to extend that result, or we're going to present the version of that result that's applicable to the discrete time case. So here is the statement of the result. Consider the discrete time autonomous system described by x plus equals f of x. Remember our notation, x plus equals f of x simply means that x at next, the value of the state at the next time instant equals value of the state at the present time passed through the function f. So the right hand side in that sense is just a one-step solution to the future. Okay, with the mapping f continuous and the origin being an equilibrium point. Okay, remember that an equilibrium point, well, the point is an equilibrium point for the discrete time system x plus equals f of x if it satisfies this relation. Okay. So that if this is satisfied, then it's guaranteed that if you start at that point x sub e, then you remain at that point for all future times. So therefore, if the origin satisfies this equation, it means that it's an equilibrium point. So let V R and R be a continuous positive definite function. Okay, therefore it's always positive and it's zero only when its argument is zero. And now we define, or we introduce this new notation. Okay, this delta v of x, which is defined as v of f of x minus v of x. Therefore, this is also a function of x. Note that this is x and f of x is the value of the state at the next time instant. So in a sense, along the solutions of the system, this simply gives v of xk plus 1 minus v of xk. So this is in a sense the discrete time version of the time derivative that we have considered for the continuous time. Okay, so this we can take as a discrete derivative. Then we have the following. First, if the derivative, discrete derivative, is negative semi-definite, then the equilibrium point, origin, is a stable equilibrium point. Okay, that is, the solutions starting close to the origin remain close to the origin for all future times. If the derivative satisfies a stronger condition, that is, if it's negative definite, then the origin is not only stable but also all the solutions, well, starting close to the origin, converge to the origin. Therefore, the origin is stable. Okay. Furthermore, if again the derivative is negative definite and v is radially a bounded function, meaning that as x goes, as its argument or the norm of its argument going to infinity implies that the function also goes to infinity. We call such functions radially unbounded. Then the asymptotic stability of the origin is global, meaning that all solutions converge to the origin. Okay. And the origin is globally asymptotically stable. Now, there's another version, in a sense, another version of this theorem for global exponential stability. Let's also write that down. Again, consider the autonomous discrete time system, x plus equals f of x. With right hand side continuous. And origin being an equilibrium point, okay, f0 equals to 0. And let this function v be continuous and positive, just like here, continuous positive definite function. Okay, and we assume that it satisfies the following properties. It can be lower and upper bounded by some constant times the norm square of the state. C2 squared, where C1 and C2, they do not depend on the state x. So that's true for all x. Furthermore, this delta v, or the discrete derivative, is negative definite, where it can be upper bounded by, again, a negative number multiplying the norm square of x. Okay. For some positive constants. C1, C2, and C3. Okay, so these two conditions hold for all x with the same C1, C2, C3. Then the origin has to be globally exponentially stable. Globally exponentially stable. Now remember that we have a tool for continuous time case through which we establish asymptotic stability through a Lyapunov function, even when the derivative time derivative Lyapunov function is only negative semi-definite. And that principle was invariance principle by Lassalle and Krasovsky. Now that invariance principle also nicely can be extended to the discrete time case. So let's also talk about that. Then we will have an example which uses Lyapunov's theory and invariance theorem together to establish some asymptotic stability behavior for some system. Okay. And this is our invariance result, which can be quite useful. Consider the discrete time autonomous system x plus equals f of x with f continuous as before and origin being an equilibrium point. Okay, f0 equals 0. Let v be a continuous positive function. And suppose the discrete derivative delta v, which is v of f of x minus v of x, is negative semi-definite. Furthermore, whenever a solution satisfies this, that is, the solution passed through this discrete derivative is identically 0. So that's only possible for the case where the solution is the solution sitting at the equilibrium point, which is the origin. Okay. Only when xk itself is identically 0. Then the origin has to be asymptotically stable. Furthermore, if v, the Lyapunov function, is radially unbounded, we have, as before, the global asymptotic stability of the origin. If v is radially unbounded, then the origin is globally asymptotically stable. Okay. Now, consider the following example where we have used Lyapunov's theorem together with invariance principle to establish synchronization of two coupled oscillators. Output coupled oscillators. Okay. So here we have two oscillators. Let's call them oscillator 1 and oscillator 2. First of them satisfies x1 plus equals q of x1. Okay, a linear system when it's uncoupled. And then the second oscillator also satisfies x2 plus equals q times x2 with the same q because they have the same identical oscillators when it's uncoupled. And then what we do is we take the output of the first oscillator and output of the second oscillator and then take the difference and use that signal to couple two oscillators to one another. Okay, and then in that case the oscillators become coupled. And when we have coupled oscillators, an interesting question or interesting problem to study is whether those oscillators synchronize or not. Okay, that is eventually, even if they start from different initial conditions, whether they converge to the same solution or not. Okay, so that's quite an interesting problem and study intensively. Okay, so now we're gonna look at that problem. Now x1 plus equals q times x1 plus lambda 1 c transpose y2 minus y1. Okay, oscillator 2, the second oscillator has the following dynamics. x2 plus equals q times x2 plus lambda 2, and lambda 1, they're the coupling strengths. Okay. C transpose is the coupling matrix, and then what we do is we feed the signal, that's the difference of the outputs, y1 and y2. Now, the outputs are defined as Cx1 and y2 is Cx2. Okay, they are defined from the same matrix, that it's meaningful to take their differences. Okay. Now, we're talking about the case where Q is in general and n by n matrix, so we're talking about that for the nth order case, nth order oscillator. A special case would be the harmonic oscillator, okay, or the discretized harmonic oscillator, where Q would be the state transition matrix for fixed period for a skew symmetric matrix, for instance. Now, if you take a skew symmetric matrix and pass it through state or compute the matrix exponential for that, what you obtain is you obtain an orthogonal matrix. An orthogonal matrix satisfies the property that its transpose equals its inverse. Okay, in inverse, Q transpose Q equals the identity matrix. C is some matrix, okay, n by n, and is the size of the output. What else? Lambda 1, lambda 2, they are the coupling strength. Okay, for our oscillators. Now we're going to make the following assumptions, and then under those assumptions, we're going to show, or we're going to attempt to show that these two oscillators, starting from our potential conditions, will always synchronize. That is, the solution x1 of k and solution x2 of k, it converges to the same waveform, same signal. Assume that the pair CQ is observable. Okay. And the coupling strength, the sum of coupling strengths satisfy this property. It's always positive, and it's not larger than the sum, it's not larger than unity. And we have some normalization assumption regarding the C matrix. Okay, C transpose equals the identity matrix. Well, this identity matrix and this identity matrix, they're different. Since Q is n by n, here we're talking about the n by n identity matrix. And since the C is n by n, here we're talking about the n by n identity matrix. Okay. Now, for this pair of coupled oscillators and under these assumptions, we claim the following. The claim is that those two oscillators synchronize. The oscillators x1 of k, x2 of k. Okay. This is the solution of the first oscillator, this is the solution of the second oscillator, and suppose that they start from some arbitrary initial conditions. Okay. And they start running. Clearly they don't behave independently because of that coupling term. The behavior of one affects the other and vice versa. And then the claim is that under those assumptions, those oscillators converge to the same signal. Okay, meaning that their difference goes to zero. Zero as k goes infinity, regardless of the initial conditions. Now let's, using Lyapunov's theorem, let's try to demonstrate this claim. Okay, now what we're going to do is, as usual, when we want to show some difference goes to zero, we try to express, or we try to obtain the system that describes the behavior of that difference, okay? So, for that reason, let's define the error signal E, which is x1 minus x2, okay? So this signal, which x1 is in Rn, x2 is in Rn, therefore this is also a vector in Rn, and this vector, or the magnitude of that vector, determines how far are the two solutions from one another, or two systems from one another. Then, let's try to figure out, if we can, the E system, okay? Now, E plus, by definition, is x1 plus minus x2 plus. This plus notation, once again, means the value of this variable at the next discrete time instant, okay? So that equals what? Q times x1 plus lambda 1 C transpose C x2 minus x1. Okay. Now, instead of y's, we write for y1 cx1, for y2 cx2. Therefore, this difference y2 minus y1 can be written as c times x1 minus x2. That c we can take out, and that produces c transpose c. Okay, the matrix here. Minus q times x2 plus lambda 2 c transpose c times x1 minus x2. Okay, so that's the difference of the right-hand sides. And that can be written as q times x1 minus x2 plus lambda 1 plus lambda 2 c transpose c times x2 minus x1. Okay, now that everything, all the states x1 and x2, they always appear as the difference, which is nice because difference is what we call in the error. Therefore, the error right-hand side depends only on the error, the difference of the states, not on individually the separate states. Okay. Therefore, we can write this as q times I minus lambda 1 plus lambda 2 C transpose C times x1 minus x2, and x1 minus x2 is E. Okay, so therefore we have the following error system: E plus equals some matrix times E, and that matrix, A matrix, is this expression here. Okay, now hence we have transformed the problem into the following. We have the claim is that the oscillator synchronize, namely this difference goes to zero. Now we define this difference as the error, x1 minus x2. Okay. Therefore, and we have shown that that system, that signal depends, the evolution of that signal depends only on the initial condition of that signal, because we have the system that describes the behavior, the evolution of the error, which is E plus equals A times E. It only depends on itself. Okay? Therefore, this claim is equivalent to the following claim. The origin of the system E plus equals AE is asymptotically stable. Okay, so we will try now to obtain that result. So for that, we're going to use the Lyapunov's theory. So for that, we have to choose Lyapunov's candidate, the Lyapunov function candidate, and let that function be simply norm square of the error. Okay. We talked about Euclidean norm, therefore, this is E transpose E is our Lyapunov function candidate for the error system. So let's see what happens to the solution of this system. And we're going to try to see that through this Lyapunov function. And for that, what we do is we compute its discrete time derivative. Okay. So delta V, which is VE plus minus VE, the difference between V at the next time instant and the present V. Okay. That equals E next transpose E next minus E transpose E. Okay. That is what's E next. E plus is AE, so what we have is E transpose A E minus E transpose E. So, therefore, that equals E transpose times A transpose A times E minus E transpose E. So let's write down what's A transpose A. This is A. Okay. If you transpose it, then what you have is this transpose times Q transpose, and Q transpose appears here. Now that this here is a symmetric matrix, therefore its transpose equals itself. So what we have therefore is I minus lambda 1 plus lambda 2 C transpose C's transpose, which is itself, times Q transpose. Okay. So therefore this thing here is A transpose, and then we have to write A, which is Q times this I minus lambda 1 lambda 2 C transpose C, and that's it, times E, and then from that we subtract the norm square of the error, E transpose E. Now, since Q is an orthogonal matrix, this here is identity, therefore we can just remove that, and what we have is E transpose times this matrix squared. Okay, this matrix squared is I squared, which is I, and then this guy squared, which is this squared, times C transpose C squared. Okay, and C transpose C squared is C transpose C. Why is that? C transpose C squared is C transpose C times C transpose C, and this thing C transpose is identity. Okay, by assumption. Therefore, we have C transpose C, the same as itself for the square. And what happens is we're left with I minus lambda 1, lambda 2, C transpose C square, this times that, minus identity, then E. Okay. So this we wrote as E transpose times identity times E, and then we can write the whole thing as a matrix that's being multiplied by E transpose from left and by E from right. Okay, so that equals E transpose times identity minus 2 lambda 1 plus lambda 2 C transpose C plus lambda 1 plus lambda 2 square C transpose C square, which is C transpose C, minus identity times E. Okay. This identity and that identity, they cancel out, and what we're left with is that equals minus E transpose 2 lambda 1 plus lambda 2 minus lambda 1 plus lambda 2 squared C transpose C times. Now, this is a scalar multiplying matrix C transpose C. So let's call that scalar gamma, and gamma is positive. Okay. Because lambda i's, each lambda is positive, and their sum is less than or equal to 1. Okay. Hence, what we have obtained is the discrete derivative along the solutions of the system for the Lyapunov function candidate V reads minus gamma times E transpose C transpose times CE, and that can be written as minus gamma times the norm of C times E squared. So let's call this equality 1. Now, since V is positive definite and this discrete derivative is negative semi-definite, okay, therefore at this point we have figured out that the origin of the E system, the error system, is stable. Okay, meaning that if you start from arbitrary initial conditions for the oscillators will not move arbitrarily far away from each other. The distance will always be bounded in some sense, and that bound will depend on the initial distance. Okay, if initially they're close enough that for the future they will also remain close enough. But that's not what we want to show. What we want to show is stronger. We want to show that eventually the solutions of the oscillators converge to zero, or converge to one another. In other words, error converge to zero. So let's see whether that happens or not. Okay. The origin E equals 0 of the error system is stable. Okay. How about asymptotic stability? Asymptotic stability. Okay. Now suppose for that, since R for the Lyapunov function, the right hand side for its discrete derivative is negative semi-definite only, we have to use the invariance principle. Okay, to establish, if you want to establish asymptotic stability. So let's do that. Suppose that some solution satisfies the following. Okay, that is the solution passed through this delta V results in identically zero output. Okay, so if this is identically zero, so that means since this is delta V and it's C times E's norm, therefore this norm must be identically zero. In other words, this product C times E must be identically zero. C times EK must be identically zero, whatever that solution is. Okay, so let's call this 2. Now if we can show that, this implies that E of K is identically zero, then by invariance principle we have asymptotic stability. So that's our next step. Now, we're considering this solution, okay? E of k, it's not an arbitrary solution, it's a special solution, and that special solution satisfies that c times ek is identically 0. For k equals 0, for k equals 1, for k equals 2, always it produces 0 output. So let's consider that particular solution. Clearly, it's a solution of the error system, therefore it should satisfy the dynamics of the error system. ek plus 1 equals a times ek, and a matrix was q times I minus lambda 1 plus lambda 2 c transpose c times e of k. This was our a matrix for the error system. So that can be written as q times ek minus lambda 1 plus lambda 2 c transpose c times ek. So that's the right hand side. Now we're considering the case where c times ek is identically 0. Okay. This is 0, therefore this term can be removed. And what we have is ek plus 1 is q ek. Okay. Now in general, ek plus 1 does not equal q times ek. Okay, it equals a times ek, and this is a. But we're not considering a general solution, we're considering a special solution which satisfies c times ek equals 0, identical. For such special solution, it should satisfy that e plus equals q times e. Okay. So that equation is equation 3. Now, 2 and 3, this is 3 and this is 2, imply ek is identically 0 by definition of observable, because we're told that the pair CQ is observable, so that means, considering this as the output, whenever you see an identically 0 output, it means that the solution is in the solution ek is in the unobservable subspace, okay, of the system. And because the system is observable, unobservable subspace is the singleton, that's the origin. That means whenever this is satisfied by observability, it must be that the solution must be sitting at the origin. Because the pair CQ is observable. Okay. Hence, whenever this is identically 0, the solution passed through the discrete derivative of the ordinal function candidate. It must be that the solution itself is identically 0. Okay. 4. Now, by invariance principle, one and 4 implies that E of k must converge to this largest invariant set, which is the origin. Okay. So we've done, basically, we have shown that the error system, the origin of the error system is asymptotically stable, therefore error is converging to 0. Okay. In fact, the error system is a linear system, therefore the origin is globally exponentially stable, meaning that the difference between the states of the oscillators, x1 of k and x2 of k, must converge to 0 exponentially. That is, x1 of k minus x2 of k goes to 0, converges to 0. And that means the oscillators asymptotically synchronize, regardless of the initial conditions.